Welcome to this video, and in this video I wanted to have a look at a very unusual feature in the spectrum of light from a star, a particular type of star which are luminous blue variable stars, and it's the P Cygni profile, and it has a very unusual feature which you can see here on the right. It has an absorption and emission line of the same line. One is blue shifted, one is red shifted, and what we're going to do is just have a look at that, why that's the case, and also what it tells us about the star itself. So because it's an unusual feature, what does it mean about this particular star? Why is this star then going to be unusual compared to other stars? So before we do any of that, we actually need to get the spectrum of the star. So in order to do this, we would use a spectrometer, but the spectrum of the star is basically just the amount of energy or the brightness of the star at a particular wavelength. And you can see that for different colored stars, different temperature stars, you get a slightly different shape. So blue stars are more heavily weighted towards the shorter wavelengths. Red stars are more towards the longer wavelengths, which should make sense because longer wavelengths have lower energy and the shorter wavelengths have higher energy. Blue stars are hotter, more energy. Red stars are cooler. So basically, this is the spectrum of the star is just the energy emitted as a function of the wavelength of light. So in order to do that, we would use a spectrometer. Now, how that actually works is you would use something like a grating or a prism, and what that does is it splits the light. So it kind of splits it out a bit like a rainbow. That's essentially what a rainbow is. And then we can work out the light as a function of the wavelength. Now, if you're doing astronomy, quite a lot of the time, they will use a combination of a grating and a prism, and it's called a grism. But the whole point of this is to split the light, and then we can get the amount of energy per wavelength, basically, which is then the spectrum. And you can do this at home, actually. You can get quite small spectrometers you can put onto your own telescope. So you can do this at home. You don't have to have a professional telescope to do this. So when you do that, you will get something that looks like this. You've got the spectrum on the left, and you can see the colors there. You get an actual image of that. But if you then plot a line profile through that, so each of those colors is going to have a pixel value. And to be honest, if you're doing this properly, you'll be using a monochrome camera, probably CCD. So you just have a pixel value as opposed to an actual color. You plot that as a function of maybe the X position in the image, and you'll get a line profile like this. Now, depending on the color of the star, it will either have more energy towards shorter wavelengths or it will be over the other side. And again, you can see that the hotter stars are more over towards the left, the shorter wavelengths, the redder stars, the cooler ones are actually on the other way. And actually, they have a lower peak amount of energy as well, so have lower energy in total. Again, makes sense because they're cooler compared to the hotter stars. So now that we've got that, we can see that the peak wavelength is going to relate to the temperature. So we can see where that actual plot is peaking, where the maximum amount of energy is as a function of the wavelength, the hotter it is more over towards the left. So we can then work out the temperature. If we can get that plot, work out what the wavelength is, we can then get the actual temperature of the star. That's how it's actually done. So for example, your green star here, that is peaking more over towards the left, so it's around about 500 nanometers. And the cooler stars are closer to like 700 or so. There's an example here for the lower ones, 700, 800, you're going to be peaking. So again, more towards the red part of the spectrum. Now this actually is part of Wien's law. So there's a fairly simple equation here for you to calculate the temperature. So from this, you could actually work out the temperature if you knew what the peak wavelength was. So on the left-hand side there, you've got the peak wavelength. So if we take the green one as an example, that is peaking around about 500 nanometers. So we've got that. And what we would actually do is we would divide that wavelength by B, which is your constant of proportionality, and then we would get the temperature. And that hopefully would give us around about 5,500 Kelvin. And you can do that for all the other stars. So that's basically how we get the temperature of the star and how that relates to the actual spectrum. But that is because stars are generally considered ideal black bodies. And a star is typically in thermal equilibrium. And if it's an ideal black body, then it's going to have the two following characteristics. So if it's an ideal emitter, then at every frequency, it's going to radiate thermal energy at a rate equal to or greater than any other body at the same temperature. So it's going to be equivalent to other bodies, essentially, of other temperatures. So something that's going to be 1000 Kelvin is going to have a similar looking spectrum to something else that is also a similar sort of temperature. Then the energy that's emitted is also emitted isotropically. It's not dependent on the actual direction. It should be direction independent, essentially, and that's perpendicular to the area that is emitting it as well. So assuming it's kind of a sphere for a star, then it doesn't matter where you're looking at that star, it should kind of all be somewhat the same. So now that we understand that, let's go back to the star and actually look at the spectrum in a little bit more detail, because we get the general shape, that black body spectrum, which gives you the general shape of it, but there are finer details in that of the spectrum. And one example is absorption lines. So between the actual main star and us, it's going to have an atmosphere that is cooler, or cooler outer layers of the star. As that energy goes through that line of sight to us, it will actually absorb some energy at a very specific wavelength or frequency. So here you've got the hydrogen lines picked out. That's assuming we've got some cooler hydrogen around the atmosphere of the star, because actually the energy is made in the central part of the star, not in the outer part, and it will absorb energy at those wavelengths. So here you've got the Balmer series, which is the hydrogen lines, and you can see you've got a very nice dip in brightness where there's a lack of light there, or there's some light that's been absorbed on its way to us. And on the opposite side, you've actually got emission lines. So most stars don't show emission lines. They're quite unusual for a star, but some will have them. And what that means is that you've got some ionized gas around the star. So this time around, the gas is much, much hotter and it's emitting at its own wavelength. So you've got the combination of the star, the spectrum from the star. You then also got the emission from the gas itself. And let's say it's hydrogen gas, which is the one pointed out here. Then you're going to get a very sharp line there for the H alpha. Then you get the H beta, etc. And this tells you that you've got ionized gas around the star that is not necessarily the main part of the star, so it's kind of independent of that. And you get these emission lines, but it is typically quite rare. And some examples here. So it could be that you've actually got a very large star that's got this extended atmosphere. It's got very strong stellar winds, and you've just got this ionized gas around, which has then been heated by the stellar wind. You've got some kind of emission nebula around that. Maybe a planetary nebula, again, would do emission lines. But what it means is you've got this hot gas emitting at its own wavelength just surrounding the star. So going back to the P Cygni profile, it comes about due to the original star in the Cygnus constellation. This was kind of one of the first stars really that was identified to have this signature, and there afterwards it's called the P Cygni profile essentially, and it's a star in the Cygnus constellation. And these are a group of luminous blue variable stars. So these are very large stars. They don't live for very long. They're going to have quite strong stellar winds, which are going to blow away some of the outer layers, which is important actually for understanding what's going to happen here. So this is what the P Cygni profile actually looks like. And it's actually a combination of an absorption line and an emission line in the spectrum of the same line. So this example here is H alpha. It's the hydrogen alpha emission of the hydrogen atom. And you've got a blue part and a red part. Now the emission line is redshifted. So it's moved towards the red part of the spectrum, whereas the blue part is an absorption line and it's blue shifted towards the blue part of the spectrum. So you end up with this very unusual combination of the two lines. So where does the blue one come from? Well, let's say we're looking at the star. You've got some extended material around the star, and it's actually expanding towards us. So it's moving towards us. It's Doppler shifted, and because it's moving towards us, it's blue shifted. It means the wavelength is squashed up a little bit, which makes the wavelength slightly shorter than if it was stationary. So it means it's blue shifted. And you get an absorption feature because it's absorbing between us and the star. So there's material that's moving towards us quite fast, but it's also absorbing at a very specific wavelength. In this case here, it will be hydrogen. And then you've got the same material doing the same thing on the opposite side of the star, but this time it's actually moving away from us, so it becomes redshifted. The wavelength gets slightly stretched because it's expanding away from us. And this time around, it's actually emitting at its own wavelength. So you get an emission line that's then redshifted. And when you combine the two, you get this P Cygni profile in the spectrum, which again is very unusual. And what does it tell you about the actual star if we see this in the spectrum of a star? Well, it suggests that it's got a very rapidly expanding hot shell of gas around it. And this is quite typical of the very largest stars we have in the universe. They have very strong stellar winds, and it means they have this expanding shell of ionized hot gas around them. So you end up with a absorption feature, which is blue shifted, and a emission line, which is red shifted. And this is an example of what one of these stars might look like. Thank you for watching, and if you enjoy, then check out some of the other videos.